Okay, so we're very happy to have Luchang Jin from University of Connecticut. Luchang did his PhD at Columbia University. He was a postdoc in Brookhaven, and he is one of the people who is responsible for the recent progress in including electromagnetic corrections on the lattice. And this is very importantly come into the recent determination of g-2, and that's what he's going to tell us about. So take it away.
Thank you for the invitation for me to give a talk. I'm very happy to talk about the lattice calculations in the muon g-2. I will give some introduction to muon g-2 and also lattice Qcd, and then talk about the two of the hadronic contributions, which are the dominant source of uncertainties in the standard model theory predictions for muon g-2. One is hadronic vacuum polarization, and the other is hadronic light by light contribution. This is the very recent announced on April 7th Fermilab results, which is compatible with previous Brookhaven results. And combined, we get this 4.2 standard deviation from the standard model predictions, which I'm going to tell where that comes from in a minute. And we also expect that in a few years, Fermilab will accumulate more statistics, and will announce much more precise results. And then if the standard model prediction doesn't change, we will have a very pretty clear signal for new physics. So what we are calculating is this vertex function. In particular, is this form factor evaluated at zero momentum transfer limits. And we also denote this quantity by this A, which is the famous G factor -2 divided by 2. So the theory prediction is decomposed into 4 parts. The first is the QED contribution. This is calculated perturbatively to 5 loops. So with very small errors. Then is the weak contribution. It's calculated to 2 loops. There is some hadronic parts in it as well, but its value is much smaller. Therefore, also eventually we get a very small uncertainty. There is some cancellations within the first 1 loop. So that's why it has a relatively small central value as well. Finally, is the 2 hadronic pieces. The first is hadronic vacuum polarization, which has the diagram look like this. We have a hadronic bubble colored in blue, and this is it has 2 additional photons attached, so it's order alpha square, and that is giving a contribution with the largest source of uncertainty at present. And the second is hadronic light by light, has 3 additional photons, therefore its order alpha cube is higher order. This is really topologically different from this hadronic vacuum polarization. And since it's higher order, so it's much smaller value with relatively small uncertainties. So let's talk about the lattice Qcd. So lattice Qcd, it can be used to calculate both these 2 hadronic contributions. We discretize the space and time and put the gauge fields on the links and the fermions on the points. We have the gauge actions and the fermion action. So once we discretize space and time, we can do path integrals over the Grassmann variables for the fermions and the gauge variables for the gauge bosons. Now the gauge boson is represented by gauge links. They are really SU3 matrices, note the vector potentials. So the integration over the gauge orbit won't diverge. So we don't have to invent the gauge fixing routines and the ghost. So we just have these gauge fields. And SU3 variables. The Grassmann variables cannot really be done on the computer. So instead, we evaluate these path integrals for the Grassmann variables analytically. So what we get is this determinants, and we try to calculate this determinant with using various numerical methods, and only doing the last step of the integral, the integration of the gauge lengths using Monte Carlo methods. So basically, we try to sample the gauge field with the following distribution: it has the gauge action and also the fermion determinant building together. This is called the dynamical simulations. The C quark effect is built into this determinant. Once those configurations, the sample points are called configurations, are generated, this effect from the from the C quark loops are automatically included. So to do this integral, once we have the gauge configuration sampled with this distribution, we just measure the observables on each of the configuration or the sample point, and we compute a simple average of them. That will be the quantum expectation value of the observable. So this is the big picture. Normally, the number of configurations is on the order of 100, and the dimensions of the path integral is order billions. So it's a very high dimensional integral, and we are using a few hundred points to calculate that with the Monte Carlo method.
Just question, so long time ago, every lattice talk I went to talked about quenching, and you're not mentioning quenching. So basically nobody is doing quenching anymore. Everybody is doing dynamical simulations. Is that more or less true?
I guess that's more or less true. The inclusions of the fermion determinant is now very, very common, and not including it will be a very special thing and worth mentioning.
Okay.
Yeah, and also one thing I guess I still need to mention is that although we do include the fermion determinant, but as you can see, the fermion determinant is included once the configuration is generated, and once we obtain the configuration, we could calculate the fermion propagators on it, but with a different action or different fermion mass, which lead to different pion or proton masses. That sometimes people can still do, especially if the fermion mass put into the determinant is slightly off the physical point. So in the lattice Qcd, how many parameters do we have? This is easy case. So if we work in the isospin symmetric limits, we usually do. And the three flavor theory, then we actually have three parameters. One is strong coupling constant, and then the light quark mass, the strange quark mass. We're supposed to take A goes to 0 limits. With the renormalization group equation, that means actually G goes to 0. So we need to have a relatively small coupling constant at the cutoff level. So really, we only have two free parameters that we can do. There is a one point correspond to the physical points, but we can simulate other points as well. To find the physical point, we need to some physical inputs. These are the pion mass, kaon mass, and usually taken the omega mass to set the scale. So we have two parameters but three inputs. Why do we need three inputs? Because one of the inputs, omega mass, is to determine the overall scale in unit of GeV. Another way of saying it is that we really just need two, the ratio of these two masses. So once we set the parameters, we can calculate something. For example, we can calculate the correlation function for the pions. we can arbitrarily introduce some pion interpolation operator, which just has the correct quantum numbers to create this pion states, and maybe some other states. But since the pion is the lightest particle, if we work on the Euclidean space-time and separate the pion source and sink operator in time for long enough distance, then the pion intermediate states will contribute the most. And once we calculate the time dependence of the correlation functions, we will be able to, for example, extract the pion mass. So let's get closer look at the process. So this is the interpolation operator. Now we need to do the path integral for the Grassmann variables analytically first, because we cannot do that numerically for the anti-commuting numbers. So we write down the path integral. We perform these Grassmann integrals. We get the inversions of the Dirac operator in addition to the determinant which we had before. And if we recall, the determinant is actually built in to the configuration generation process. So what we need to do is to calculate these Fermi propagators on the already generated gauge configurations, and we calculate this propagators for each of them and average the results. And sometimes we use diagram to represent these formulas. We use diagrams which look like Feynman diagrams, but these lines, the Fermi propagators, really means the inversion of the Dirac operators evaluated with the gauge field diagram. And therefore, we have automatically include all the gluon interactions between quarks and also gluon interactions with the C quarks. That is the part of the determinant. Here is the sample calculation. Is an example of the pion effective mass calculated this way at large enough t that we'll just give the pion mass. This is one of the RBC Qcd ensembles with 2.359 inverse Jeff lattice. The pion mass is at physical point.
Can you give me an idea, just roughly, like how many sites are there on a point, and how far away are you measuring the 2-point function, just to get an idea?
Thank you. That's the next question. So this ensemble is called 64I. So for the spatial direction, it has 64 points on each direction. So X, Y, Z direction. On time direction, usually we double that so that we can have a longer range, since we study in many cases study the time direction correlation functions. So time direction is 128.
Okay.
And here, this is the in lattice units time in separation in lattice units. So you can see that around 10 already it seems that mostly it's pion states, and we can measure very precisely up to, for example, 60. That's really half of the time extent. Beyond that, there will be most contribution come from the other direction because it's a periodic boundary condition.
Right. Thank you.
Thank you for the question. Then let's talk about this hadronic vacuum polarization contribution. So there are in the old days there are two ways to determine it. Both use the experimental input. One is use the E plus E minus annihilation process, and that will involve a virtual photon, and then the virtual photon will go to a lot of hadron final state. It could go to hadron final states. And if we measure the total cross section, including photon radiation as well, then we can write the dispersion relationships to obtain the hadronic vacuum polarization contribution to muon g-2. So this is actually the method which gives the standard model predictions that we mentioned before. There's another way, which is using the tau decay, which emits a W boson and then goes to hadrons. The experimental accuracy for the tau case is also pretty good. It's at least comparable to the E plus E minus annihilation process. The problem with that is that we need to do isospin rotation for this process to actually with actual hadronic vacuum polarization. And that rotation, isospin rotation, is not very reliable because of the isospin breaking corrections, which is related with the rotation. We can try to use Lattice Qcd to calculate this isospin breaking effects. This was proposed quite some time ago, and this hasn't been finished yet. So at this point, tau decay data is not included. We just have this dispersive method for the E plus E minus. The lattice calculations to determine the HLbL was started very long time ago. This is 2003. I think this is the first paper to use the lattice. At that point, this is a quenched calculation, and this is done by my colleague now, Tom Blom. At that point, he was also at BNL National Lab. So later, at this, from our group as well, we had this is a complete lattice calculation, include the QCD plus QED effects as well. Things to get required accuracy. Even the leading order HVP, it has the photon within the hadronic blob. That effect should be considered as well. So it include that contribution. It include also strange, charm, quark contributions, and adding all that get this value. Is 700 times 10 to the minus 10. Uncertainty is on the order of 20. This is 4 or 5 times larger than the result obtained through the dispersive analysis. On the other hand, we can actually take a portion of the lattice data and combine with another portion from the dispersive analysis and obtain a combined value. And that value is pretty precise because the lattice overall value is very noisy, but some portion of the lattice is actually precise. It's pretty precise, and we can replace that. We can use that to replace part of the experimental data and improve the overall accuracy. This value actually agrees with the pure dispersive analysis. More recently,
can I ask a question? Is there some way in which, well, maybe you're going to talk about this. I mean, I mean, my point of view is it's incredibly important that, in a way, it would be very good to have accurate results that you didn't have to combine, right, from the lattice and from the experiment. And even better, it seems like in principle the lattice could check some results from the experiment. I mean, not just the value of the g-2, right, but there are lots of other things in the data that you could try to calculate and try to see if there's agreement, right? Because this is just such an important thing. So I wonder if you have any, if you're going to comment on any of that.
I try to do that. There are a lot of very nice checks, including the ones that you just mentioned. And especially now we have, we actually have quite a few discrepancies between the lattice and also between lattice and experiments, and also between different experiments. There are discrepancies here and there maybe.
These experiments are pretty old, right? I mean, and there,
right.
You know that there's this effort now to do electron muon scattering, where you have a much more clean system. You have a T-channel photon exchange, and so you can really, you know, directly measure the thing in the space-like region, and it's a modern experiment and so on, right?
Right. That is actually a very nice design. So I'm aware of that. But that experiment, I think it's very much on schedule, but
Yeah,
we
it's the
haven't get the
future.
result yet.
Right.
Yeah, presumably by the time that Fermilab have this final numbers, that experiment will also have the results. So recently there is a BMW results. This is really a pure lattice result, and the accuracy is getting to the point which very much comparable with the dispersive analysis. But interestingly, the value it obtained is kind of in the middle of the BNL or Fermilab experimental value for the g-2 and the dispersive analysis for the HLP. So it kind of have a few 2 sigma deviation from only with the previous dispersive analysis and 1 point something deviation with the full g-2 measurements. We'll see the comparison figure later. So let's see how we actually calculate HVP on the lattice. The major thing is that we calculate the current correlation functions, which is the HVP diagrams, look like this, the hadronic part. And then to account for the rest of the contribution to get g-2, we need to integrate this correlation function with t, times this w, the weighting functions, sum from 0 to infinity. And the integrand, the combined w and c, the correlation function, will look like this. So you see that most contribution are between 0 and 2 Fermi. So this range is where the most contribution is coming from. Coincidentally, this is also the energy range. If we convert this Fermi into energies, is happen to be on the muon mass, but that is really a coincidence. This is the curve will still looks like this if we are calculating this HVP calculation to electron muon g-2 or the tau muon g-2. This peak is mostly come from the pi states or the rho resonance states. So this peak is kind of mostly come from that. In fact, if one just use the rho mesons to write this current correlation function, one can mostly get the behavior, except at long tail, it has a pi states, which can be described by KPT with some accuracies, deviate from this rho meson. And the weighting function, I can also describe a little bit. The weighting function can be calculated analytically. So its form is known back in 2011. And in this Mayer-Berniker paper. And at relatively short distance, so it's in the short distance limit, the weighting function behaves like t to the 4th. But all this region can be kind of viewed as short distance region. It has to be very long before it reaches long distance region, that in which case it becomes t squared. And this deviation is kind of happens at here. So the rough behavior, we can think that the weighting function just behaves like t to the 4th. This picture is really showing the lattice data, and this curve is converted from the R ratio, which is the dispersive analysis. You can see that roughly that has a pretty nice agreement, and you can also see that the lattice points has larger and visible error bars at relatively long distance, where the R ratio value is pretty precise.
Have you, sorry, can I ask a question? So, you know, these dispersive approaches, the data is of course not in the same kinematics as the the diagram, right? Here, when you're doing it on the lattice, you're exactly calculating the correct field theoretic quantity, right? Because it's a Euclidean time, and you can literally write it as an integral over Euclidean time, right?
Right.
But for the dispersive approach, you have to take some data that's in the, something like a time-like regime and go into the space-like regime, something like that, right?
Right.
And so, I mean, like the deviation around t equals 3 or so. I mean, first of all, is that the main source of the deviation, or or is it near 0
Um,
between go ahead.
the near 0, this is really just lattice fact, because this is the first lattice size.
Yeah, right.
This is really pure lattice fact artifacts. And here, this is likely mostly due to the statistical error that lattice calculation have. The most problematic region is really in the bulk, but the deviation is not very large. So from this picture, it's not very visible. And also comment on the rotation from the time-like region into space-like region. That rotation is very reliable, and it can only work one way, which is from the time-like region that experiment measures to the Euclidean time region. If we want to convert this curve to the experimental measurements, that's very hard and not very.
Right, because it's kind of a damping, right? Going into Euclidean space is a kind of smoothing, right? Right.
Yeah. So convert the experiment into the space where lattice can measure, we can very reliably do, but the inverse is a very hard problem. So this is a more detailed comparison, where we can decompose this total contribution into 3 pieces. The 3 pieces is that we can just write the weighting function into 3 pieces, where the 3 pieces add up to be the full thing. The first piece is the short distance piece, which looks like this. And this is the window piece. It's between the short distance and long distance. It's the remaining piece account for this part, and then the long distance pieces. So this is in the space where we do lattice calculation, and then we can also convert it into the time-like region where the experiments do the measurements. And you can see that the most pi peak is captured by the window, and the window is from 0.4 Fermi to 1.5 Fermi. And with some smearing function so that it's not a sharp cutoff. And and also there is for the experimental side, there are this E plus E minus annihilation process measured from many different groups, and mostly there is Barbara and Chloe are relatively accurate, but they have some tension in this region. And in theoretical prediction that we have for now, we account for some systematic error was accounting for this tension. The difference by lefting out each of them will give a difference which is 5.6, and we divide that difference by 2 and gives 2.8. That is the additional systematic error, which is try to accommodate this tension in the analysis. However, if we replace this portion which has some tension by lattice, it is much less affected by this tension, and the lattice data is sort of in between and kind of closer to Barbara, which is a little bit larger than Chloe. And we'll have more comparisons on the windows later.
Sorry, these windows are this window is just some arbitrary way that you are breaking up the calculation so that you can combine it with the experimental determination. So you're trying to use the lattice for just the part that the lattice is accurate, and then using the experiments for the other parts. Is that the idea?
Yes, exactly. You completely get this.
Okay.
This is a complete arbitrary decomposition, and we can do any decomposition we like. We just try to get this region where the lattice is pretty precise.
Okay.
Right, for long distance, the lattice has larger statistical errors, which is harder to deal with. So how do we get the lattice value itself more accurate? There's a few methods. So first of all, so the initial formula we write here, we have a 1 point fixed and the other point summed over to give the time-dependent correlation functions. But of course, to get more statistics, we want to sum over the other point as well. So for example, we want to sum the other point over the entire space-time on the lattice. That will be the most ideal thing, but it's cost prohibitive because we need to do an inversion to calculate the fermion propagator if we want to measure any points. So calculate the fermion propagator is an expensive operation, and we cannot afford to calculate the fermion propagator for each lattice site. That's too hard. So instead, we use some techniques to help to achieve the similar statistics with much less cost. The first step is so-called almost averaging. This is trying to say that when we calculate the propagator, it's using an iterative method. The method called conjugate gradient. It's an iterative method. So if we don't go to the full precision, we can save a lot of iterations. And then the idea is like we truncate the iterative process to obtain the so-called sloppy propagators, and only use a relatively a subset of the sloppy propagators and also calculate those propagators accurately. And we can estimate the difference between sloppy and accurate propagators. Actually, the correlation function calculate from the propagators, use the small set of the data, and then we can have a larger set of data to just have the sloppy propagators, and that gives us more statistics. So this is one great way to increase statistics or reduce statistical error. Another important method is called low mode averaging. If we recall, a fermion propagator is inverse of a sparse Dirac matrix, and we can calculate the eigenvectors for that Dirac operator, and that the most important eigenvectors is the ones with smallest eigenvalues. Therefore, when inverse, when we try to calculate the inverse, that's become the most important part. So we can approximate the inverse of that matrix just using its most important modes, that's the low modes. And then if we use that approximation, we can easily repeat this correlation integration for the entire lattice size. But then we have this bias, which we correct using the point propagators we have calculated in the previous method. So it now becomes the 3 generation, the lowest accuracy ones, but we really do the full volume summation is the low most. And then we have a sloppy propagators on a larger set of points, on set of points, but a larger set. And then the smallest set is we calculate exactly, and we calculate the bias generation by generation. So the final effect is that as if we calculate all the points exactly, but with much reduced cost. At this point, it seems that this is already the best we can do, but actually we can do even better for longer distance. For the longer distance, we have the largest noise. The way we do it is by recognizing at the longer distance, we can decompose the contribution into the sum of all intermediate states, and then the correlation function is written as a sum over all the contributions of different intermediate states. But when T is large, high energy intermediate states contribution decrease very fast. Therefore, the most important contribution at long distance is only a few lowest energy eigenstates, physical states. So we can just try to calculate the energy of those states and the matrix element for those states. And that will be able to allow us to reconstruct the long distance behavior for arbitrary long distance and the relative error don't grow. And so that requires us to study the spectrum for the pi system in the I=1, j=1 channel. But if we study the spectrum, it allows us to reduce the statistical error beyond the gauge noise limit. So that's really nice. So there are some plenary studies. It's a while ago, but still, currently we haven't had any published result using this method. So once we had the published result using this method, you can expect accuracies from lattice, especially a statistical error, reduced by a lot.
Can I just get this? I'm curious about this. Like, what kind of accuracy can you get for, say, the lowest energy splitting? Like, what kind of accuracy is an accuracy that starts to be interesting for getting to be able to improve this, to make this improvement? Like, do you need them to 1%? Is it okay to get it to 10%?
That's a very, very nice question. So we can look at the plot to see how well we are doing right now. So the black curve is the direct evaluation. And these few color curves is just include 1 state and 2 state and 3 state and 4 state, full state contribution. So you can see if you look at this this portion where the value is the largest. This is integrand, by the way. Then you can see that the energy of the states and the coupling, the matrix element, is not calculated very accurately at all. At this point, we have very large visible error bars. However, these error bars will decrease proportionally at a longer distance. But the direct evaluation has error bars growing with that. So if we only try to calculate the long distance part with this method, then we can reduce the statistical error by a lot. But for the relatively short distance, we still use the direct calculation. This is really just trying to get rid of this very small long tail, but with the direct method, it's very noisy. But this itself is the small portion of the data. So the relative error for the spectrum study don't need to be very high.
Okay.
So this is the major ways that to attack the hardest part of the problem, which is this connected diagrams with light quarks. The light quark can go to long distance, therefore we need to evaluate long distance has large noise.
Sorry, can I ask another question? So, I mean, should I be surprised that, like, the red curve, it looks like you're doing pretty well with just 4 states. So it looks like, if you could get those 4 states to better accuracy, you could maybe even start competing with just getting 4 states looks like it's already getting, kind of close to the full lattice simulation.
Right. It's very hard to get more states though, and with 4 states, it's already approximate entire spectrum very well, especially at long distance. It's because high energy states really has contribution decrease very fast at long distance because it decreases exponentially.
So maybe I see. So maybe this quantity that you're plotting here is already, so it's sort of dominated at t equals 10, right? And so, but t equals 10 is what in physical units? I mean, is that already pretty long distance compared to, I don't know, a GeV or something?
That's about 1.2 Fermi or so.
What's a Fermi again? I mean, sorry. I mean, I know it's very roughly, but I want to know, is it a few GeV or is it a fraction of a GeV inverse? I don't remember.
That's the inverse of 1 Fermi, I think, is about 0.2 GeV.
0.2 GeV. So it's already pretty long distance in a way.
Right.
Okay.
So if we recall the pion correlation functions at similar distance, that's almost completely dominated by the ground state.
Right. Okay. Okay, thanks.
And also on the lattice, the number of states depends on, because it's the pi system, the number of states depends on the volume. And with the volume we have, this is a 5.5 Fermi box. This is a reasonably large box to contain pions, but if we have the periodic boundary condition which we have, the first moving pion state actually have a pretty large energy compared with the rest of pion. So then if we just go to higher the excited state, the energy increases pretty quickly. So then we can to get the required accuracy, we need to not only calculate these most simple diagrams, but it's also the hardest diagrams. We need to calculate the correction as well. So there are a lot of diagrams that has the photon propagators and also related with the strong isospin breaking. We need to calculate all of those. Some of them for some reason, because of SU3 flavor symmetries, that they are very small. But most of them we need to calculate them. But they are explicitly suppressed due to the photon propagator and the QED charges and the up-down quark methods. So although they are more complicated diagrams and there are a lot of them, but with the explicit suppression, they are relatively easy to get to the required accuracies. So this is the summary plot. This is the combined value of lattice and the R ratio. This is just R ratio, which enters the white paper, the theory values, which I showed in the beginning of the talk. This is 2R ratio calculation, doesn't enter the white paper. Here are a lot of different pure lattice calculations. Most of them with relatively larger error bars. Roughly, it seems that the pure lattice results are kind of higher than the R ratio, but with larger error bars, I guess one cannot really tell. But one noticeable value is from BMW. It has relatively small error bars comparable to the R ratio, but it's considerably higher than the R ratio and closer to the full G-2 measurement. So this is really raising some questions on whether the BNL experiments really find the new physics or just find a mistake in the R ratio calculation. Which
could I ask, did your value, you described this window function thing, so you are actually using some experimental data in your result as well?
Yeah, this value.
If you tried to give a pure, did you give a value?
That's what I give here.
What's
that's
that?
This value. That's this value. This is the
so you have a much, okay. So that was my question. It's a much larger error.
Right.
And the central value shifted.
Right.
Right. Okay.
Yeah.
Okay.
But with this large error bars, the central values here doesn't imply very much.
Yeah. Sure.
Yeah. But BMW's value is very interesting. So we'll discuss more of that. So first of all, the question we can ask is that what happens if we just look at the comparison on the window, which is of course this is mostly on the for the lattice people to compare. So this is trying to replace the window value by the RBC lattice. But what if we use other groups' lattice results? So here is that comparison. This is RBC Qcd results. And we can see that there is some tension here as well. So RBC Qcd is using domain wall fermions. ETMC is using Wilson fermions. And all the above is using staggered fermions. So roughly it seems that staggered fermions somehow tend to give larger values, but it's not a firm statement. And also at this point, these three values are using the same set of ensembles. And FHM is Fermilab, Qcd, and muc. They are using also the same set of ensembles. This is the muc ensembles, so they are rightfully using these ensembles, and also a little bit more ensembles they have. BMW is using staggered fermions, but with a different version of the staggered fermion. So this is a comparison on the windows. You can already see there's some tensions. So among the lattice, things do not agree perfectly yet. And all the groups, for example, RPQCD, are trying very hard to improve this windows, and we are planning to hopefully to publish the new window values in the next few months. So hopefully we'll try to improve the current situations by telling whether there is
so can I understand if Aubin et al., it looks like their window error is a little smaller than yours. So you're saying that if they had used the window method and they believed everything, they would quote a smaller, even slightly smaller error than what you guys are claiming.
Exactly. Yeah. And also you can see that there are two Aubin et al. Values. And this is just this is a extrapolation using 3 lattice spacing that they have, and this is just using the 2 finest lattice spacing, and then gets a slightly larger error bars. So it's very tricky to estimate the systematic effects in the continuum extrapolations.
Yeah,
and this is really a problem for all the calculations. That is a very tricky issue. So I would say the cross checks between different lattice formulations and try to have more lattice spacing is very important. One particular thing which you might notice is that the BMW value, well, this is really the same BMW data set they use to have the super precise final values. But for this window, it doesn't seem that it's much more precise than other points, in particular the RBC point. The reason is that the BMW value here is mostly from their estimation of the systematic error. So I mentioned before that the long distance part really have a lot of statistical errors, but systematic error wise is less clear. So BMW somehow estimate to have a larger systematic error for the window.
Can I ask? I mean, from your previous thing, it looked like you had if you didn't use the data, you had this huge error bar. So if the only difference between that much bigger error bar and the one that you're claiming is the use of the data outside this window, right? Is that it? Or is it also, because you also mentioned these extrapolations using the long distance behavior from the excited states. It's really all of that, I guess.
Right, that's all of it. Okay. So really
but the reduced stuff outside, it's all the stuff outside the window, right?
Right.
So I mean, that suggests that together with this plot suggests that whatever BMW is doing, they're somehow claiming to get the stuff outside the window much better than anybody else on the lattice.
Yes.
Right? That's the key, that's the takeaway message. Well, a takeaway message. I can take that away.
Yes, I guess you can take that away. And and also it's the reason that they managed to get the part outside of window very accurately is very simple. They use they use this method to improve the signal, just like everyone else does, but they have a much larger set of configurations to average over. Currently, no one has actually used this yet in the published result, although people are developing the methods. And also, unlike many other error bars here, which although the size looks similar, but most error bars here are mostly statistical error, except BMW, which is dominated by systematic errors, because they managed to reduce the statistical errors to a much smaller value with a huge set of configurations. So this is the continuum extrapolation, which is a large source of systematic errors in this lattice calculation. For the window, this plot we are seeing is for the window, and it's BMW's value. This curve is the pure lattice curve, and this curve is using lattice data and combined with some calculations for trying to reduce the leading order discretization effects due to the taste breaking phenomenon that one has for staggered fermions. And they have different ways to do the extrapolation, and with this spread of the results, obtain this systematic error. And you can see this is away from the R ratio and the RBC QCD results, which is a more complete comparison is the previous slides. And then we also have their they also have this continuum extrapolation similar, but for the entire light connected contribution. And in this case, the continuum extrapolation is mostly done for the ones with corrections. The one without correction, if we extrapolate, we'll get a quite off result. That's because at longer distance, the taste breaking effect is more important, and there's a I guess correcting that is really important. So I guess without correcting, the extrapolation is maybe is more problematic. So if we do this, we will get much off value, which is even higher. So then we can also compare the individual contributions. BMW gives the values for each type of diagrams, and for example, in RBC QCD also give contributions for each type of diagrams, and some of them agree well, but some of them does not. For example, this particular diagrams, there are some discrepancies, and so this also needs further study and more cross checks. And the nice thing is that the cross checks are possible. So we can calculate individual diagrams. They are individually well defined and they can be cross checked. Summary. This is the computational time cost for the RBC's published results, and the BMW's calculation actually presumably costs much more computer times for their most recent results. The next RBC UK QCD result will have 4 times more statistics than the previous ones, and also include a third less spacing. So that hopefully will the next publication will focusing on the window and will hopefully tell something that about the tensions on the window. So the summary is that for the HVP, we just need a handful of inputs. The lattice with this handful of input parameters can give the HVP contribution to muon G-2. The bottleneck is really just the leading contribution from the light quark connected diagrams. This is the leading contribution, and it's also the bottleneck. And the statistical error is mostly come from this part, and also the systematic error is also here, which is a process of continuum extrapolation. That is very hard with taste breaking, and also without taste breaking effects, it's also not very easy. So cross checks with different lattice calculations by different collaborations using different fermion formulations I guess will be very useful to resolve those puzzles and reduce the systematics. Also cross-section on the subleading diagrams, which are relatively easy, but there are so many of them, so avoid an actual mistake. To have this cross-check would be very, very helpful also. So that's all for HVP. For the light by light, the diagrams is on the order of, it's high order, but this diagram is more complicated diagrams. They are analytical approach, which have a very has improved a lot compared with, for example, 2009. But then the central value doesn't change very much at all. The major uncertainties for the analytical approach is for the high energy states. So for the lattice,
sorry, isn't the analytic result just some stupid quark model? It's not even, I wouldn't say it's an analytic calculation. I would say it's a quark model calculation, isn't it?
It has been improved since the initial days. So nowadays is trying to use the dispersive approach to define the contributions from the lowest energy states, the cuts in the diagrams. So unlike HVP, which we can write the entire contribution in a single dispersion formula, we cannot do that for light by light because it has too many lags. Still, for some specific channel, we can write the dispersive relationship, different channel, write different relationships. So for the pi naught and eta prime poles, that can be defined very cleanly for those type of contributions. And also for the pion and kaon loops, it can be defined also relatively cleanly, and also involve the pi scattering. And this part nowadays is with the recent development from the dispersive analysis, is done reasonably well. However, the difficult part is that beyond these lowest states, the heavier states contribution is harder to estimate. But it seems that they doesn't contribute a lot anyway. So this is the major source of uncertainties, but it's also very hard to do with this approach.
Okay.
Yeah. So this is the unreliable pieces, and it's also contribute a lot of uncertainties. On the lattice, actually, is the opposite situation. It's kind of this state is the most problematic ones. So these two pieces are kind of complementary, but it's also not very easy to combine them because of the two complicated diagrams.
I'm sorry, but I have to go. So thank you very much.
Oh, thank you.
Sorry
that ran a little bit time.
Yeah.
But
no,
the light by light, yeah, thank you. The light by light calculation is more complicated diagrams. We have a lattice calculation, and we spend a lot of efforts to try to be able to deal with these complicated diagrams and at the same time reduce statistical errors. Because if we are not careful, it can easily have too much statistical errors. And we also calculate the disconnector diagrams. And this is the lattice we are using. And we calculate the connected ones, disconnected diagrams, combine them, doing the extrapolations to infinite volume and the continuum limits. And we estimate all kinds of possible systematic errors. So we get we're testing the method of doing the extrapolations with the pure QED values, and that is has a very nice agreement with the analytic calculation. So finally we obtain this value, which is this 7.87 with larger statistical errors. Compare the errors is larger with compared with the analytical approach, but the source of the errors is very different. So I think it's a very nice confirmation for both results that this will tell us that we have very little room for the light by light to explain the discrepancies. Now the major doubt is presumably the HVP. Also, this calculation has cost about 1 billion BGQ core hours. It's mostly performed on mirror. And also very recently on the same day where the experiment announced the values, the MINES group, which has been working on the light by light calculations for a very long time with us, independent from us. And they are using a method which is in major part is very similar with us, but it has some also very nice difference. So their systematic errors is also quite different from our results. In particular, they use infinite volume QED, so their final volume errors will be very different. But also they are performing the calculation with unphysical biomass, so they have additional errors in the chiral extrapolations, systematic errors. So the systematic is very different, and they managed to control the statistical errors and obtain a more precise values. At present, this value is the most precise one, although one can argue whether the systematic errors, how to estimate them. And RBQCD also trying with the infinite volume QED approach, which by itself is very nice. And this is our preliminary results with also a problem with how to estimate the systematic effects. This is the summary for light by light. And that's everything. So for the lattice errors, we have statistical error, we have disqualization error, we have final volume errors, and sometimes if we are doing a non-physical biomass calculation, we have chiral extrapolation errors. And the Lattice Qcd is starting to play an important role in determining muon G-2, and we can expect more results when the Fermilab releases their final results, so we can resolve the puzzle, hopefully. Thank you very much.
Okay, questions?
I have one question. How long do we need to wait until we know the final answer, either from a theoretically or from new data, something like that?
That's a very good question. For light by light, although I guess it still takes some time to get to even this value is not enough. It's not accurate enough to compare with the final Fermilab's precision goal. But you can imagine that we can continue to improve, and it's unlikely the value will shift very much. So that doesn't seem to explain the precision, the discrepancies. On the other hand, the HLbP result is quite tricky. So we can look at this comparison. There are actually new experiments planning, both for the E minus E plus, which are ongoing. So we may expect this dispersive approach to improve. Also, Marcus mentioned that, as Marcus also mentioned, that there is a different type of experiments, the muon E experiments, which is a very different experiment, has doesn't have the complexities that we have in these ones. So that experiment will also have a very nice check on the HLbP contribution. Certainly, just the pure lattice, BMW have already showed that just the lattice calculation can get to a very small error bars, and most other error bars are statistically dominant, but this one is actually systematic error dominant. So the statistical error can be reduced, and the systematic errors is more tricky. But you can see you have many different lattice groups here, and they are using different fermion formulations. The major systematic error here is disqualization errors in the continuum limit extrapolation. And different lattice groups are using different disqualization errors because of different action. So having a cross check with different groups when they both improve the accuracies and also add more lattice spacings to reduce to make this the continuum extrapolations more reliable. So that will hopefully reduce this, clear this puzzle. And it's hard to say a firm timeline, but maybe we will have some very nice news in a few months when we have our updates on the window value, so we can have a better comparison in this plot.
Okay, that's very nice. Thank you.
Thank you for the question. Do you have other questions? So by the way, so for the RBC UKQC side, the HP calculation is led by Christoph Lerner. He was at the Brookhaven for quite some time and working on this, but recently moved to Regensburg in Germany. My role is mostly focused on the hadronic light by light calculations, but I spend most of the time talking about the Christoph's calculations and also other BMW results, because that seems to be the most interesting part at this point to explain the discrepancies.
Okay, if there's no other questions, let's thank the speaker again. You can turn off your
Thank you
microphone.
for the invitation and listen to the talk. Thank you very much.